Hi, my name is Alina, and in this presentation I will be presenting the paper Hypercube, which is a paper that is focused on creating a high-dimensional hypervisor fuzzer. First, a quick overview of the paper. It was written by Dr. Shumilo, Dr. Aschermann, Dr. Abizi, Dr. Werner, and Dr. Holz, and was presented at the NDSS Symposium in 2020. In this paper, they are looking at current hypervisor fuzzers that are out there and saw that there's kind of like a lack for them. So they created a high throughput fuzzer design, which they then tested on a large number of hypervisors. And fuzzing these hypervisors, they found more bugs and coverage than other hypervisor fuzzers. Before I get more into the paper, I want to give some background. I want to talk about virtual machines, hypervisors, and fuzzing. Understanding these things makes it easy to understand the paper, so I'm just going to give a quick overview. I'm going to start with talking about what a virtual machine is. So, a virtual machine is a virtual emulation of a physical computer, and it can run essentially different operating systems in an isolated manner. So let's say I have a Windows 10 laptop. That is my Windows 10 is my operating system, my host operating system. And on that operating system, I can run other operating systems. For example, if I want to run Linux, I can run Linux. If I want to run Windows 8, I can do that. And all these virtual emulations are isolated and they run on the host operating system. And there are different uses for virtual machines. Since it is like an isolated system, it's often used for sandboxing or malware analysis, because if you run the malware on a virtual machine and like it somehow infects the operating system, it won't actually affect your host operating system, just your guest operating system. And it is also used in the current multi-tenant cloud infrastructure that we see. So whenever certain companies are offering an infrastructure for service, they're most likely using virtual machines to provide that infrastructure for their clients. To actually run the virtual machines, there's another component needed, which are the hypervisors. Hypervisors is a software that the multiple operating systems can actually run on a single physical machine. And the hypervisor essentially manages the hardware resources and allocates them to the virtual machine. So if you look at the left, it's this very simplified image of that we have our physical hardware, and the hypervisor is taking those resources and allocating those to the different operating systems. And on the right, I have just a screenshot of the VirtualBox hypervisor. It's from my own VirtualBox. We can see that it has different operating systems that it can just load up, but VirtualBox is the actual hypervisor that is managing the bridge between my host hardware system and the virtual machine system. So now that we have an idea of what virtual machines and hypervisors are, let's go into the threat model that happens in this situation. This is the threat model that is assumed in the paper and kind of reflects on how the researchers designed their fuzzer. Let's say there is a malicious actor that gains control of the kernel of a virtual machine. It then can try to get control of other virtual machines that are running on the same hypervisor. And if it can get control of those, it can get control of the hypervisor and the host operating system itself, or even the server that the host operating system is running on. So for example, if you have that cloud infrastructure that I was talking about earlier, all that data that is on that server is at risk. So if it's other clients that are using that server, using that infrastructure, their data is at risk because another virtual machine on that server was attacked. So now let me briefly go over what fuzzing is. Fuzzing is a software testing technique to find bugs, vulnerabilities, and unexpected behavior. So let's say you have a target system. We can just take an example of a program that takes a input and does something with that input and creates an output. So we have this target system, and then we identify inputs that it could take. We then generate this fuzz data and execute the target with that data. And then we just try to see what the program does with it. Does it exit normally with it? Does it call an exception? Whatever it does, we're trying to monitor that. And if there's any defect or any crash, we want to log that. So essentially, fuzzing is a way to find vulnerabilities by just trying many different inputs, just throwing a lot of inputs at the program and seeing if any of them cause a crash. And if they do, we can trace it back and see which input caused a crash in the system, meaning, and therefore showing what vulnerability it had. There are different types of fuzzing, but I'm only going to go over two that are like relevant for this paper. One of them is black box fuzzing, which you can kind of understand, kind of like get a sense of what it is from the name. So essentially, the inputs that you're generating for the program are not based on anything about the program. So you do not know anything about the program. It's a complete black box, and you're just trying random inputs and hoping that something will stick. You do not learn from any of those inputs. You're just trying to throw random inputs in there and hoping to get something back. And should some of them result in a crash, you will find a crash. So now, what do you think gray box fuzzing is? I already gave kind of a hint. It's also called coverage guided fuzzing. So after you generate an input and run it through the program, you might be able to find a crash. But in the cases that you don't find a crash, you have some type of output. And this output updates the coverage data. So it can see if your test case, your input, increased the coverage of the program. Like, was it in any way meaningful for the program? And if it was, if that input was meaningful for the program, like it actually executed more code in that way, did more covered more lines of the code, then it will be added to the corpus. And this is like an ever-growing seed pool from which then more inputs will be generated from. So this is more a smarter fuzzing way, so there's actually logic behind which inputs you are feeding to the program, because you're trying to use inputs that are like close to something that has already caused a crash. So now that we have an idea of fuzzing and we know what hypervisors are, the question is, why is fuzzing hypervisors so hard, and why were there at the point of writing this paper not that many hypervisor fuzzers out there yet? So the main problem that comes with fuzzing hypervisors is that hypervisors expose many different interfaces, and vulnerabilities often require very specific sequences of interactions across those multiple interfaces. So we can't just test the interfaces individually to find a vulnerability. We often need to find a specific sequence to get to a vulnerability. Another problem is that there is hypervisor interfaces that are undocumented or poorly documented. So for a fuzzer to generate realistic and meaningful interactions is difficult when there is no clear specifications. And the final thing is that hypervisors are very long-running and stateful systems most of the time. Additionally, also, rebooting a hypervisor or a virtual machine is very slow. So if a fuzzer does find a crash, it usually takes a lot of time to get the system running again. Additionally, initialization code may hide bugs, and hardware acceleration can introduce non-deterministic behavior, which makes it difficult to trace back what input caused a vulnerability if you can't really replicate that again. So let me briefly show again what the attack surface is and how that causes a problem. We have our guest virtual machine on the left, our guest operating system, and our hypervisor on the right. And in the threat model, we are assuming that the guest operating system is malicious. So everything it does is attacker controlled. So whenever the guest performs a privileged instruction, which does happen quite a lot when using a guest operating system, and these instructions include like I/O instruction, access memory mapped I/O, triggering DMA, or making a hypercall. This causes a so-called VM exit, and this means that the control leaves the guest operating system and jumps into the hypervisor. So now the hypervisor needs to emulate that operation. It has to decode the instruction, it has to interpret the parameters and simulate the hardware behavior. And if there is a bug in that logic, then the attacker may be able to escape the VM and execute the code inside the hypervisor. This is where the threat model comes into play. Like if one of these privileged instructions causes the attacker to, or the malicious actor to break out of the guest system into the hypervisor. But usually if it's not causing that, after emulating the operation, the control just goes back from the hypervisor to the guest. But yeah, this is an overview of the attack surface, a little bit more detailed, showing that there are many different ways how the guest interacts with the hypervisor and how this could be an attack surface. Next thing I want to talk about is some previous hypervisor fuzzers, and there's especially one hypervisor fuzzer that the paper mentions a lot, which is called VDF. At the point of when the paper was written, this was the state-of-the-art hypervisor fuzzer. It's an AFL-based gray box fuzzer, so it's a coverage-guided fuzzer. The key idea behind VDF is to manually extract individual device emulations from a hypervisor and then fuzz those components in isolation. So this is kind of limiting it to low-dimensional fuzzing, and in practice it mainly targets MMIO interactions. So instead of fuzzing the entire hypervisor, it focuses on specific device emulators one at a time. This improves coverage inside those individual devices, but it has two limitations. First, it tests devices in isolation, meaning it doesn't exploit sequences across multiple interfaces, what I was talking about earlier. And second, it does require manual extraction of each device, which limits scalability. So this is what, when the paper was written, what the state-of-the-art hypervisor fuzzer was like. And this leads us to the topic of the paper, where they created a new fuzzer, a new hypervisor fuzzer called Hypercube. Hypercube was designed around 3 core goals. The first design goal of the Hypercube was to have a high-performance fuzzer, and they do these by introducing 2 core components, a own custom operating system and a bytecode interpreter that is built into the operating system, and I'll get into those components in a bit. The operating system helps decrease the time it takes to restart the guest operating system after each crash, since it's a very minimal operating system. And the interpreter helps a lot with increasing the throughput. The second main design goal was to have a high dimensional interface coverage. So the fuzzer VDF targeted mostly one interface, primarily MMIO. And Hypercube instead models fuzz input as a sequence of operations across multiple interfaces. So they want to fuzz all the I/O stuff, the MMIO stuff, DMA stuff, and hypercalls, all those privileged instructions that I was talking about earlier that could cause a VM exit, or that cause a VM exit. And finally, they want to focus on having a stable and deterministic execution. So by building their own operating system, they remove any interference that could happen. They fully control the memory layout, the page tables, and interrupt handling. So any crash is reproducible and fuzzing feedback is stable. And I was kind of talking about them a little bit, but talking about the core components of the Hypercube, we have the Hypercube operating system, which is a minimal custom operating system that runs inside of the virtual machine. So it takes almost no time to boot it up, and it does not have a lot of additional just stuff. Then they have Tesseract, which is a custom bytecode interpreter, which I'll get into more later in the presentation. And finally, they have like external host side tools for like logging, minimization, and decompilation. So let's get into the architecture of Hypercube. So we have our hypervisor and our VM, and that VM is run on the Hypercube operating system. Its main job is to enumerate available interfaces, like the MMIO, the I/O ports, and managing memory. After booting, the operating system launches Tesseract, the custom bytecode interpreter. So Tesseract consumes arbitrary byte streams and interprets them as sequences of hypervisor interaction. And finally, we have the host side external tools. So the minimizer is trying to minimize crashing inputs. The logger logs all the crashes, logs anything that's happening in between in the fuzzer. And the decompiler is used to decompile the bytecode into readable C code. So to understand, like let's say a crash happens and you have that input byte stream, the decompiler will help decompile that and make understand what, in like human readable code, what caused the system to crash. So after all this architecture is set up, we have a input that is provided to Tesseract, and that is just a byte stream, and it will interpret this byte stream as a sequence of guest level operations. And if one of these operations requires privilege handling, the CPU triggers a VM exit that I was talking about earlier. So it controls the transfer to the hypervisor, which will emulate the request operation. And this is where we're trying to see if that input causes the hypervisor to crash. The external logger always like passively records the serial output from the virtual machine. So if the hypervisor crashes or the VM becomes unresponsive, it's detected and recorded. So now that we have like an overview and high-level overview of the architecture, let me go a little bit deeper into the Tesseract interpreter. So as I was like mentioning a little bit earlier, it takes any random input and converts it into a valid program. It helps interact with multiple hypervisor interfaces, so it actually has these like sequences that I was talking earlier about that happen a lot when using hypervisors, and this way you can actually create those sequences to find those vulnerabilities. And it also uses scratch memory to make data structures and pass pointers, helping it like to do more complicated interactions. So let's say we have this like random byte stream right here. It will go to Tesseract, and that will like interpret into like an actual sequence of valid instructions. So it's a valid program. So after creating Hypercube, they tested it on like these 6 hypervisors. So yeah, they decided to use to fuzz with Hypercube on these hypervisors, and the results were that they found over 55 bugs. The most common ones were assert failures, but also quite a lot of null pointer dereferences and memory corruptions, but also like divide by zero exceptions and deadlocks. So after finding these 55 bugs, in the evaluation of their paper, they kind of go off of 4 research questions that they want to answer. And the first research question they have is, did Hypercube uncover new bugs and new vulnerabilities? And it did. They tested 6 hypervisors and found over 50 bugs, and already have been assigned 43 CVEs from these bugs that they found. And as I was showing in the slide before this, those bugs included memory corruption, deadlocks, and assertion failures. And this demonstrated that Hypercube was quite effective and quite effective in finding previously unknown vulnerabilities. For their second evaluation question, they were trying to see if Hypercube was able to rediscover old bugs and vulnerabilities. And it did rediscover 4 known CVEs, and it found all the bugs that VDF, the other state-of-the-art hypervisor fuzzer, and they also noted that like Venom, which is a vulnerability found in Chemo's virtual machine, it was a pretty prominent CVE. It discovered this bug in like under 10 seconds, while the original fuzzer that found this bug took over 1.5 hours to find it. For their third research question, they wanted to compare Hypercube with VDF, the other state-of-the-art hypervisor fuzzer that I was talking about, and wanted to compare it in coverage. It outperformed VDF in a lot of things. In the like 15 experiments that they did, Hypercube was able to find or to have more coverage in 13 of those. It also found, it also crashed in 9 of those, while VDF only crashed in 4 of them. And for each run of these experiments, Hypercube only took about 10 minutes until like it found a crash, while VDF took about 60 days to fuzz this and get to the same conclusion. And for the final research question, they were examining performance of their fuzzer. Hypercube's custom operating system and interpreter allows like very high throughput, which is like 2,300 times faster than a compiler-based approach. It also has a very fast reboot after crashes with only 0.22 seconds versus like 2.3 seconds for like a minimal Linux system to boot up. And the memory footprint is also quite significantly lower than like for a Linux system. And these design choices are all like directly contributing to the efficiency of the fuzzer. The paper also discusses potential future work and also limitations of Hypercube. First, it currently doesn't use coverage guided fuzzing, which is one of the main design choices that they made to actively be a black box fuzzer, but they did mention that perhaps using a coverage guided fuzzer, like kind of transforming Hypercube to use coverage guiding, could help improve testing for very complex devices with like deeply nested conditions. Hypercube only has very limited support for Hyper-V and para-virtualized devices, since these require very like specialized communication channels. And the final limitation that they mention is it cannot boot in 64-bit EFI mode, which restricts some hypervisors. So these are some limitations that come with the Hypercube, and potentially future work could erase those limitations so that Hypercube is even more effective and more general. Finally, let me come to my conclusion about Hypercube. Hypercube is a generic high-throughput black box hypervisor fuzzer. It found 54 bugs across multiple open source and proprietary hypervisors, and it outperformed state-of-the-art coverage-guided fuzzers like, for example, VDF. And this marks the end of my presentation. Thank you for listening. I hope you have some interest now in reading the paper for yourself. Here are my references, and yes, Thanks again for listening.